Hi, I'm Mr. Richmond. This is your Unit 13.2 lesson summary. Unit 13.2 will be on congruence in math, congruence in geometry. And we'll do one problem here. It's a pretty short section, but we need to know a couple symbols and how they're used in geometry. So let me start by talking about a few of those. First is our angle symbol, which will look like this. If I'm talking about an angle, angle A, it'd look like that, angle A. Now if I start to have more to it, like let's say I have an actual shape, and this is A, B, C, I can specify an angle a little more clearly by saying if I want to talk about angle A here, it could be angle B, A, C. So I'm saying the direction I'm going, starting, middle, end, and I can start to specify angles. That becomes important in later topics in geometry, because now if I say angle A, I don't know if we want BAC, CAD, or if they mean the whole thing, BAD. So there's a lot of options. So we have to specify it more by using three vertices to define the angle. When I talk about a segment length, let's say now I want to talk about segment AB. I use AB with a segment symbol over it to talk about segment AB. If I want to talk about segment AD, I say AD and I put a segment symbol over it. Now I can also talk about the measures of it. Let's say AB had a length of 8. Well, if I took a ruler to that and I actually measured AB, I would use a little m with the segment and say measure AB. If I was given what it equals, I can also just say AB without the segment length equals 8. If I'm talking about an angle, if someone tells me what the measure of angle A is, or I use a protractor and measure it, then I can say the measure of angle A equals 40 degrees if I'm giving a statement about what it actually equals measurement-wise. So just kind of a quick overview of some symbols in math and geometry and what they mean. Now, let's just say, for example, that the measure of angle A is exactly the same as the measure of angle C. If that's true, then they are what we call congruent. And when things are congruent, it means they have the same measure. So I can then state that that angle A is congruent to angle C. So if I can prove their measure the same, I can now say that they are actually congruent. I can do the same thing with side lengths or segment lengths. If I said AB is equal to BC, but they're the same measure, then I can say that segment AB is congruent to segment BC. So it's really just more about the language of geometry here that we'll be discussing. So let me get into an actual example and give you an idea of how we might quiz or test you on your knowledge of this. And we'll do that by writing congruent statements like this. So here I give you a shape. It's ABC, it's a triangle. I wrote the coordinates in case it's hard to see the actual coordinates on the graph there. And then I have a new triangle, DEF. And what I might ask you is how I could have transformed ABC to get to DEF. It could be a translation, it could be a rotation, it could be a reflection. And you need to be specific. If it's a rotation, what type of rotation? If it's a reflection, what type of reflection? If it's a translation, how is it translated? Look at how it's mapping. If it was a rotation, I'm going to rotate like that. If it's a reflection, you'll see it reflecting over distance-wise. So my A is maintaining the same distance as D, my C is maintaining the same distance as F, and my B maintaining the same distance as E. You can also tell from the coordinates. Only the Y values are changing signs. That recognizes a reflection. So I can tell that it is a reflection. I do need to specify exactly the type. It is a reflection over the x-axis. As for the congruent angles and sides, I just have to make sure as I map the reflection that I match them up appropriately. So angle A, angle B, and angle C are the original angles, and I want to recognize what they're congruent to. If I map it over, the position that A is in would go to where D is. So now angle A is congruent to angle D. B would map all the way over, it's the farthest one away, so it should stay the farthest one away from the reflection line, so it maps to angle E. And angle C maps over to angle F. As for the corresponding sides, it's a lot easier to write once you have the angles. So I have a segment AB, that's my vertical segment. It's going to be congruent to what appears to be DE, which you have to write it the right way, so I want to make sure they match. AB, DE, I have to keep the consistent order. Next segment is the base, AC. AC, when reflected, matches with DF. AC is the order, so DF is now the order. And the last segment is my slant segment, BC. It should match the slant segment in the other one, which would be E to F, and I can check with what the angles say they're congruent to get that. So segment EF. Now that I have the congruent angles, the congruent sides, I can write the congruence theorem. So triangle ABC, and I can write that CBA instead, but I went with ABC, so I need to match that this way. And that can be tough by looking at the picture, so match it here. A to D, B to E, C to F. So triangle D, E, F. Just like that, you got it.